graphing them, again, without the inspire. You don't need them anymore if you know your parent graphs and your transformation rules. If not, come on in for some extra help and practice. So here we go with day 9. If you look at the beginning of this problem, it says, and read the directions, to graph a complicated looking function without an inspire, or any calculator for that matter, we must first determine the parent function. As always, math is consistent. We've been talking parents since the beginning. Then break the function down into individual transformations. Don't forget to follow order of operations. So here we go with sample 1. We're going to graph g of x equals 1/2 absolute value x plus 3 minus 7. Well, the function name that I said was absolute value, the thing without the numbers really. So my parent graph is the absolute value of x. Its anchor point, like all of the anchor points of the 4 most common parent graphs, is 0, 0. Okay, so what you want to do now is graph that parent. So I'm going to move to the bottom of my paper and graph absolute value of x parent. And again, you should be getting really quick at these after all of our practice and pop quizzes and study time. There's its anchor 0, 0. And there's its other side. Okay. Now, following PEMDAS, we want to think about what we should do next. Well, PEMDAS says parentheses first. We don't have parentheses, but we do have other grouping symbols. Same thing. That's why some of us have changed PEMDAS, parentheses, exponents, multiply, divide, add, subtract, to GEMDAS for grouping symbols. I think that's really helpful in cases like this. So, the next thing we're going to do is look inside those grouping symbols, and we see absolute value of x plus 3. Now, that x plus 3 in our grouping symbol is a left-right transformation. In this case, it's a left 3. So we're going to do a translation left 3 units. When I move 0, 0 left 3 units, my anchor point becomes negative 3, 0. So I go back to my graph, and I take my parent graph and I move it left 3 units. I'm going to change colors so you can see the difference. Okay, new anchor point, negative 3, 0. Label it. Okay. For the next part, we've taken care of in PEMDAS our G, our grouping symbols. Exponents don't really apply. If we saw an exponent, it'd be telling us our parent, x squared, x cubed, and so on. Then we need to multiply or divide in order from left to right. Well, here I have 1/2 times the absolute value of x plus 3. That's multiplication. That's what I do next. So my next graph will be y equals 1/2 times the absolute value of x plus 3. Now, that's a dilation of 1/2, which is our vertical shrink back toward the x-axis. When we dilate, the anchor point does not move. So my anchor point stays negative 3, 0. Multiplication does not move our vertical distance. So we come back to our graph, and remember that with a vertical shrink, we take the distance from the x-axis and multiply by our dilation number, in this case 1/2. This point is no 0 distance from the x-axis, it stays put. 1 is 1 away from the x-axis, this becomes 1/2 on both sides. This point is 2 away, half of 2 is 1. Same here. And what you can start to do is notice the pattern, and it's easier to deal with even numbers when you're taking half than odd. So I'm going to skip and think about kind of slopes. Up 1 over 2, up 1 over 2, up 1 over 2. and that makes up 1 over 2, up 1 over 2, up 1 over 2. That's dilated my graph, done a vertical shrink of 1/2. Okay, the last part is a -7 at the end. Well, that's adding or subtracting. That's the last thing I need to worry about with my PEMDAS. So we're going to graph y equals 1/2 absolute value of x plus 3 minus 7. That -7 at the end is a horizontal translation. Because it's a minus, it's down 7 units, which means my vertex, or my anchor point, moves down 7 as well. So my final anchor point is -3, -7. So finally at my graph, I take my anchor point, -3, move it down -7, and I'm translating this entire red graph, this already dilated red graph. So when I made that graph, I went up 1 over 2, up 1 over 2 because of the dilation. Translations don't change shape. So from that anchor point, I can do the same slopes. Up 1 over 2, up 1 over 2. In both directions. And there is my final graph. Now the instructions say label each graph A through D respectively. You can certainly do that. Here is my parent A. Here is the translation left B. Red is my dilation, part C. And my final graph is solid, and I use black ink again, that's part D. Again, if you use colors, you can just make that last graph nice and bold. You can label it final. You can grab a highlighter and make it really obvious. It's up to you, whatever makes you feel better about me being able to see your work and your steps. Okay, I think there is one more and we will be done. Our second sample problem. Y equals 2 times x minus 3 cubed plus 4. Okay, well, my parent graph, I see x is being cubed. That's my parent graph. Y equals x cubed. Anchor point of all 4 common parent graphs are 0, 0. Go to your graph and plot your parent x cubed. And again, these parent graphs really need to start going quickly if they're not already. And note as I look at pop quizzes about x cubed, it's a nice smooth curve. It's not a bunch of line segments, so be careful with that. You want accurate graphs all the time. Okay, again, following PEMDAS or GEMDAS, I have a -3 in parentheses, so that's the next thing I graph. X minus 3 cubed. That is a translation to the right 3 units, which means my anchor point becomes 3, 0. Take all of your points and translate them 3 units to the right. Okay. Outside of my parentheses, I have 2 times that. Multiplication comes after parentheses in PEMDAS. This is a dilation by 2, which is a vertical stretch away from the x-axis. Again, with dilations, anchor points don't change, so it will stay 3, 0. So I take this red graph, measure distances from the x-axis and double them. This point is 1 away. 1 times 2 is 2. This point's 8 units away. 8 times 2 is 16. It's up there somewhere. I can't fit it. It's okay. 0 stays put. 0 times anything stays 0. This distance of 1 away stretches to 2 away. And again, this 16 I can't quite get to, so we estimate that. and connect the points we do know for sure. And you can see the thinner or narrower graph because of that vertical stretch. Oops. The last step is a +4 at the end. Addition and subtraction comes last in PEMDAS. Addition and subtraction in an equation is a translation up 4 units, which moves my anchor point up as well. So my anchor point goes from 3, 0 to 3, 4. And I take my most recent graph, my black stretched graph, and I move all of its points up 4 units. Anchor point up 1, 2, 3, 4. So 3, 4 is my anchor point. From that anchor point, I was able to graph over 1, up 2 in both directions. Over 1, down 2. And this is a classic example of these graphs getting messy. And that's going to happen, and it's okay, as long as we can follow your work, whether it be color-coded or labeled steps or whatever. And while I'm sure you thought it would be impossible that you could graph anything without a calculator, as long as you know parents and transformations, and now you know you can. That is it. Have a great night.